So far we have been doing relatively easy molecular orbital diagrams of compounds with hydrogen as the ligands, right? We've been focusing on MO diagrams for compounds with central atoms and then pendant ligands. And so why are the hydrides, right, one with hydrogens, why are those relatively easy molecular orbital diagrams? It's because the orbitals that are involved in bonding are very limited. For your salts, you only have to create salts of the 1s orbitals, right? Hydrogen only has one valence electron, only one s orbital, 2s is too high in energy, 2p is too high in energy. Once you start getting to more complicated situations where you have p salts, or you could have d salts or f salts even, then that can get more complicated. So we're going to slowly walk through this example, and this is really the one time we're going to do it in lecture. There are some homework problems that will guide you through some other, more advanced molecular orbital constructs. But this is the one time in lecture we're going to slowly go over an example with more complicated salts. So we are going to successfully derive the molecular orbital diagram for carbon dioxide. Looks like a pretty simple molecule. So first things first, identify the point group. We know that this is a linear molecule, right? And so point group's going to be D infinity H because we have a C2 going right here, and it's linear. All right. Now we got to make salts of the pendant atoms. So what orbitals are involved in bonding here? We have oxygen ligands. For oxygen, we're in the second row of the periodic table, so we can have 2s orbitals and 2p orbitals. Both of those are available for bonding. The 2s salts, it's the exact same case as what we derive for beryllium hydride. We can represent s orbitals. Bonding through s orbitals is going to be through sigma bonds. That's going to occur directionally, which we can represent through vectors that just show electron density pointed towards the central atom. It doesn't matter if it's a 2s, 3s, 1s, it's all the same, general shape, sphere. And so we could go through the math, but we're going to get the same thing where we have two salts because we started out with two orbitals, right? Two s orbitals, right? And the symmetry we figured out last time was sigma G plus plus sigma U plus. The sigma G plus is the top one here where they're in phase. Sigma U plus is the bottom one here where they're out of phase. So far, so good, and not too bad. Now we get to the 2p salts. And the 2p salts are different. And the way that they're different is, well, for one thing, there are 3 of them, right? Or there's 6 of them, 6 salts, but there's 3 atoms, right? 3 orbitals, px, py, pz. And then since there's 2 atoms, there's 6 total atomic orbitals. 6 total atomic orbitals is going to give us 6 total salts. And the way we're going to represent p orbitals is vectors, just like we did with s orbitals, but these are going to be in their respective directions. So the y orbital is going to be, I'm defining it as pointing up. X and y definitions don't really matter. As we've talked about, it's really your z definition that you have to watch out for, right? Your z definition has to be consistent. That has to be lined up with your principal rotation axis. So in this case, lined up with your C infinity. Our px is going to be like this, is how we've defined it, and our pz's are going to be like that. So we have z1, y1, x1 for the first oxygen, and the same 2s for the second oxygen. And now I'm pulling up the D infinity H character table, and we have a similar situation here with which is what we did for the 2s orbitals, but we have to make a 6 by 6 matrix effectively, right? And so just to be clear, what we're doing here is we're going to be asking, for this 6 by 6 matrix, what happens to all of these vectors, right? And so we are asking for a 6x6 matrix, and we know that we're trying to transform x1, y1, z1, x2, y2, and z2. And what do they transform to? Well, we're doing identity. Identity, of course, none of them change. X1 goes to x1, y1 goes to y1, z1 to z1, x2, etc. None of them change. And so we know the matrix here is going to be the identity matrix. Hopefully by now you're very good at this. If you can't do this at this point, you need to talk to me, right? But you're going to have zeros across the board on the other side, on the non-diagonal. So then we take the sum, 1 plus 1 plus 1 plus 1 plus 1 plus 1 equals 6. So that gets us a character of 6. We're coming up with our representation for the 2p solids. Next, we are going to do the C infinity. Now, I've used block matrix multiplication to break this up for the off-diagonal elements. So the Z1s here, so C infinity. C infinity is going here, right, through there. So we're spinning this along the Z. And so it's a little, let's just think about Z1 and Z2. Z1, Z2, they're in the axis, so they're not going to move. So Z1 and Z2 just go to themselves. But now we're doing some arbitrary angle. So I'm just calling it phi. It could be infinitesimally small, right? Because it's C infinity. And so we need to use the rotation formula. Go way back to chapter 2 for this formula, right? And so we can do that both for x1 and y1 to transform those, and for x2 and y2. Now we're going to take the trace of the matrix. And what's the trace going to be? Well, the z components are going to give you a 1 each. So that's going to give you 1 plus 1, gives you 2. But then you're going to have plus cosine, phi, plus cosine, phi, plus cosine, phi. That ends up being 2 plus cosine phi. So it looks a little funky, but that's what the character is. And now we're going to do the sigma v. So sigma v, again, is going, that contains, it's any mirror plane that contains the Z1. It looks like here I chose one that kind of runs, let's see if I can draw this, that runs here. Well, that wasn't a great drawing, but basically I drew kind of a diagonal mirror plane. And so what's that going to do? It's going to take x1 goes to y1 and x2 goes to y2, and it contains z. So here's your molecule. Here's like straight y, here's straight x. I chose it to go in between at a 45-degree angle. Again, it doesn't matter what you choose. You could choose the YZ plane. You're going to get the same thing. And so, you know, that caused some things to change. Z1 didn't change and Z2 didn't change, so I got a character of 2. And that might have been a harder one to choose. We could choose, let's just so you guys are clear, let's choose an easier one here. So let me, there we go. Okay, let's choose an easier one here. So let's just do one in the ZY plane. I can draw that, right? So if you do it in the ZY plane, what is that going to do? So that's going to be different than these. That will take things in the front and take it on the back. So x1 is going to go to negative x1. Y1 is going to stay the same because it's in the plane. Z1 is going to stay the same because it's in the plane. X2 is going to go to the negative. Y2 is going to go to itself, and Z2 is going to go to itself. So our matrix here, we have a negative 1, a 1, a 1, a negative 1, positive 1, sorry, and a 1. So add all those up together, and you're going to get 2 again, which is what we had. So, you know, this is the beauty of group theory, really, and this idea of the characters, that it doesn't matter how you define your x and y or what plane you use or what symmetry you use, right? In this case, right, we have infinity sigma v's, but it didn't matter which one we chose. We could have chosen some complicated off-axis one. We'd still get the same answer of 2. Inversion. Inversion turns out to be 0. How does that work? Well, remember, it just goes negative of everything. So x1 is going to have to go negative x2. How does that work? We're in the left-hand side of the molecule in the front. And so we're going to have to go to the opposite of that, which is the back on the right-hand side. So that's going to be negative x2. y1, that's up high to the left. We're going to have to go down low to the right. That's negative y2. z1, well, that's to the right, and so we're going to have to go to the left. And vice versa for all these. So they all end up changing to another vector or a negative of another vector. So there's going to be all zeros on the diagonal of your matrix, so that gets you 0. Okay, S infinity is very similar. We have an x1 here. We're going to do a C2 first. And so doing a C2, that will flip you in into negative x2, right? You're doing a 180-degree rotation. And then let me draw that. And then I chose a mirror plane, that same diagonal mirror plane. So I'm at negative x1. Oh, sorry, 180-degree rotation. We are doing, yeah. So x1 is going to go into y2. We have a 180-degree rotation. Sorry, this was correct, what I wrote. 180-degree rotation, we're spinning it. So that's going to get us to negative x1. And now you're doing a sigma h, right? Well, where's the sigma h? Sigma h is right there. It's cutting through the molecule, so it takes things to the left and goes to the right. But anyway, you can walk through all of this, and you know, essentially, you're going to get 0. There's a lot of different ways to define this, because you can do just a little bit of C infinity. Looks like actually I did a 90-degree rotation. That's what I did. I did a 90-degree rotation. I can do any degree rotation I want, right? I want x1 to y1, then I went to y2. Sometimes I have trouble remembering, you know, what I did, because there's so many different combinations you could do on these. But anyway, you could do a 180-degree rotation. That would take negative x1 into negative x2 after you flipped it. Either way, it's going to change into another vector or some permutation of another vector. So you're going to have zeros on the diagonal all across the board. C2s, again, same idea. You do a C2, there's a perpendicular C2. So you're swinging this x1 around into something else. Okay, so those are all going to change. There's an infinite number of them again, so it depends upon which one you change. But it's going to be 0. So I'm going to stop there, because now we have actually our reducible representation. Next, we're going to talk about how did I get to this step. Next step is to reduce it, right? You have a reducible representation. You're going to reduce it. So that's what we're going to do.